Let's consider another property of our conductors. Suppose we have an isolated conductor, and that conductor has a charge Q on it. Now remember, our conductor is an equipotential. That means every point in the material of the conductor is at the same potential. And let's choose phi of infinity to be 0. Then we can say that this equipotential value, phi, and now what we like to establish is the relationship between the charge that's carried on this conductor and the potential. They're related. And what we do, they're linearly proportional, so the charge is proportional to the potential with respect to infinity on that conductor. Now, the constant of proportionality is called the capacitance. And so what we have is that an isolated conductor has capacity to store charge. And C is the capacitance. And if we look at our SI units, that the typical capacitance in SI units is called the farad. And 1 farad is equal to a coulomb per volt. Now, recall that a volt is an energy per charge. Remember our definition of potential difference. So what we have here is a coulomb, and that's volt, remember, is joules per coulomb. I'll just look at it like that. And a joule, now we can put our, signify this, we'll use the C squared for coulombs, divided by a joule, which, remember, a joule, if you want to think about that as just energy, it's a kilogram meter squared per second squared. And so we have this complicated relationship where we have coulomb squared, second squared, kilogram meter squared. And sometimes we denote this by an F for a farad. And that is a description of the capacitance of an isolated conductor with a charge Q. We'll now look at some examples. We talked about that capacitance of a single isolated conductor. Now let's consider what happens if we have 2 isolated conductors. So here's one, and here's another. And these isolated conductors have, one has a plus Q, where Q is positive, and the other has a minus Q. Now that's very specific to this pair of isolated conductors, that they have equal and opposite charges. And remember that we'll call this conductor 1 and this conductor 2. And this conductor is an equipotential surface with potential phi1. And this conductor is an equipotential surface with phi2. This arrangement of 2 isolated conductors held at different potentials is what we call a capacitor. Now, there are many special cases of this, which we'll examine in detail: parallel plates, coaxial cylinders, concentric spheres. But in general, what we mean, this is called a capacitor. And the definition of the capacitance here is C, capacitance, times the potential difference between these 2 plates. And we always want our capacitance to be a positive value, so we write phi1 minus phi2, even though in this configuration we expect phi1 to be at a higher potential than phi2. So this is what we mean by a capacitor. And for examples, we can consider the following. We can have a very long plates with plus Q and minus Q. The plate has an area A and separated by a distance d. This is what we call a parallel plate capacitor. And we could have concentric, very long cylinders where the inner one, say, has plus Q and the outer one has minus Q. This is a concentric cylindrical capacitor. We could also consider spheres of different radius, different hollow conducting shells of radius R1 and R2, we can put plus Q and minus Q on those shells. And this is an example of a concentric spherical capacitor. And for each of these capacitors, the capacitance will be different. It will be a property of the result will only be determined by the geometric properties of these objects. Clearly, the geometric properties are very different. So there's no one formula that describes the capacitance of every set of two conductors. And so now we'll work out the capacitance of each of these three cases.